It's me again. Hi. This presentation is about assessing the pull-out and pull-off strengths of fixings in GRC products. This piece of work we are still doing actually started about almost post the 2015 conference, following conversations with manufacturers and within the GRCA technical committee. I would say from a personal point of view, I used to be involved in manufacturing GRC back in the 80s, and perhaps we didn't know a lot, but one thing we sort of did was keep things simple. And what we've noticed in the last 10, 20 years is that the fixings that go into GRC or onto GRC have just become so complicated, to the extent that many manufacturers and others have said to me, the hardware on the back of a GRC panel is actually costing more than the panel. So we need to look at this and decide, have we actually got this right? Is this an aspect we just overlooked? We thought, what we used to say in engineering, PPI, put plenty in, is that going to sort of be the solution? So, beg your pardon, I've got to work out how to use this thing again. Right, here we go. So the aims and objectives were very simple. Firstly, to establish suitable methods for testing fixings embedded in or attached to GRC. Obviously, there are no standard methods available in terms of standards being written for GRC. There are methods available, and that's what we've done effectively. It's not rocket science. We wanted to understand the variables which are key to the performances of the fixings. We wanted to generate some performance data. We originally had the idea that we'd come up with a nice little design matrix, which when we got into it, we realized it was far more complicated and we couldn't do that. But we could establish some basic rules for good practice. So we split it into a number of stages. They weren't necessarily run in consecutive order because sometimes we had to loop back and do a few more tests to see what happened if we changed a variable. But effectively, we developed a suitable test method. We wanted to develop a mixed design that we felt we would be practical to use in manufacturing, but also give us some sort of standardization in terms of the testing we were doing. We wanted to study the parameters which influence the strength of the fixings attached or embedded in a piece of GRC. And we wanted to see if we could optimize the design of the fixings. And as I say, especially the last part is still ongoing, because although we might have, you'll see, come to some conclusions on the fixings we embed or attach to a GRC product, we haven't really moved on to the bracketry or any of that. So that's where we're at. This just illustrates basically, I beg your pardon, I'll just press the button. This just illustrates sort of the fixing mechanisms that could take place. So if you've got a situation like in the top three diagrams, what we're basically saying is, that's how the fixing itself could fail. Well, clearly, if you've got your mathematics right, you're never going to have a fixing that fails. It should be easy to work out the strength of the steel, and hence you shouldn't really be failing the fixing socket itself. But when it comes to embedding it in a piece of GRC or attaching it to a piece of GRC, there's some sort of unknowns which we wanted to look into. So firstly, we looked at what happens, say, how does it fail if we look at a pull-out type failure. And clearly, when we embed a fixing on a piece of GRC that's attached to a piece of sprayed GRC, the most likely failure is in this area here where you have this discontinuity. So that's what's happening in a premix effectively. I think also, by the way, a lot of people out there, they don't realize when they're designing this. I mean, I know the mature designers like Smart Crosby who are here today and Charles Rickard, etc., they all know that GRC is not a homogeneous material, especially when it's sprayed. But we see a lot of little drawings where people just draw something and they just assume that you've got the same material throughout, which isn't the case. So when we spray, as you know, we end up spraying in layers, and then we come along and we make a bonding block or pad and we stick a fixing onto that, and we attach that to the back of that sprayed GRC product. And of course, right here in where that red line is, we've got a discontinuity, which is the most likely place for it to fail. So we played around to start with different testing jigs. I apologise that to some of you might say, well, why the hell do they do it like that? Whatever. But we needed to start somewhere, and although there were pieces of equipment out there that could easily apply a pull-off force, What we wanted to do was to make sure we were testing the right thing. We wanted to actually test how the fixing came out of a piece of GRC and how that piece of GRC failed. And we didn't want a mechanism for testing that interfered with that failure. So these are the rigs. I'll come back to those in a moment. These are the sort of failures we were getting. So you can see when we embedded it to a shallowish depth, we got this sort of classic, rather elegant kind of failure of a cone of GRC material pulling out of the GRC product. But when we didn't make our embedment block big enough, we basically failed the block. So you can imagine if we kept increasing that size of fixing, we wouldn't have actually got any increase in strength, because all that would happen was we'd have just been splitting the block, so we'd have just got the same result all the time. So anyway, we narrowed this down. I'm going to have to skip quite a lot of work, what we did, because obviously this, as I say, goes back over about 8 years. And we came up with two test jigs. The one on the left was for doing a pull-out test, and the one on the right for doing a pull-off test. But fundamentally, we use this same piece of equipment, which is a HydroJaws, I don't know what you call it actually, HydroJaws pull-off test. And I'll just show you here, if I may. There you go. A little video. It's always nice to see a bit of television. So we had this ring against which the specimen was pulled, and you'll see in a moment cracks developing radially away from the fixing, and you'll also discern a little bit of doming in the area of the fixing. So you can see it's cracking the block, but at the same time it's pulling it up. So we did, as you can see, have some radial cracks that protruded out to the edge of the block, but ultimately we felt that this was a valid way of testing these fixings. We also adapted the test, or this was really the test unadapted, so we could do a pull-off test. The only thing we changed here was that this load platform, if you want to call it that, it looks a bit like a little oil rig really. We just made that bigger because we wanted to make sure that the legs weren't interfering with the failure mechanism. But on the other hand, we wanted them close enough to the bonding pad so that we weren't putting flexure into the GRC product, because if we put too much flexure in, that would also affect the result. So again, little bit of a video, and you can see here we've almost got the sort of perfect balance between pull off and pull out strength, because you can see that bonding pad is actually starting to fail. Anyway, that's pulled off, and that basically concluded that part of the testing. So we got a jig which wasn't perfect. What you're seeing here is more the sort of perfect result after a few years, but in the early days we played around with some different formats, which if we had all day, I'd show you all those different types of jig that we tried. So having got a jig that worked, we then wanted to establish a mixed design in which we could embed the fixings. It was very apparent from talking to manufacturers that although you see specifications where it says the GRC around the fixing should be the same as the GRC in the product, you do not want to do that. If you're spraying with 5% fibre and you give the guys well, whatever. I mean, I've seen guys trying to spray the material around the fixing. Now, how the heck is that ever going to compact around the fixing? So in the end, just about everybody said, well, we spray into a bucket and then we take some of the fibre and we mix it in, and they kind of guess it in by eye, which is fine. So we decided, obviously from a research point of view, we've got to control that. So we looked at pulling out of blocks of GRC with zero fibre, about 2.5% to 3%, where we chopped it from the spray gun. And we also looked at a mix that was as high a fibre level as you could get, sort of grade 18, as the GRCA would call it, GRC. We also looked at using a typical premix GRC with 2.5% of short 13mm fibres. So initially we made up some pretty crude blocks. We decided that this 200 by 200 millimetre diameter by about 100 millimetres deep would be okay, and we just suspended the fixings in the middle and cast or hand packed the material around it. And For whatever reason, may or not, with hindsight, probably wouldn't have done it this way, but we took some M12s, which our friends at CFS, Tim Chart, kindly lent us. I don't think we ever gave them back though, did we? And we pulled those out of these blocks, and kind of not surprisingly, really, less was more, as we say. As we went up in fibre content, we did increase the load-bearing capacity of the one with the pin, but the one with the disc welded on the bottom, which we called a stud anchor, didn't really change that much. But when we actually cast it into a premixed GRC, where we were sure of good compaction around it, the load-bearing capacity kind of shot up. I haven't shown the results for 0% fibre. Forgive me, that was a mistake on the slide, but the results came out at about 12 kilonewtons. So I'm sure someone was going to ask that, so there you go, that's the answer. So having got those data, we decided that really there weren't many practical situations where we would need to use an M12 fixing and have sort of 50 odd kilonewton load capacity. But our recommendation for the mixture that should go around fixings has come out at, we think that, we think this should be recorded somewhere as a guidance for GRC manufacturers and specifiers, that when you make a mix to go around a fixing that you're putting onto a GRC product that's sprayed, you do not want to put 5% fibre in, you want to mix with about 2.5 to 3% fibre. If you can measure it all out accurately, that's fine, but you could probably just do it by volume. Okay, so as we said, the test demonstrated that the load-bearing capacities of the M12s were far in excess of the typical requirements for most GRC applications. So we then decided, well, you know, M12s cost more than M10s, so let's do some testing on some M10s. So again, our friends at CFS kindly gave us some different fixings, and we tested them. So we had some, you can see here, some different base plates. We had, I'm sure, I won't tell you what the trade name is, I'm sure you're familiar with Big Head. But we had some Big Head fixings. We had with little holes in the plates, which some people thought that the holes might help it bond better. We could dismiss that, forget it, nothing's going to help you like a little hole in a little plate. We then made up, because we wanted to look at other parameters, we made up different fixings. These are just a few of them, where we had little base plates and we made up the fixings. And what you can see is that the base plate type or size really didn't make a lot of difference, but what did make a difference was the height of the fixing. So a 30 millimeter compared to a 20 millimeter, the pull out load increased substantially. Just for the sake of getting a lower reference point on the range of things that people might use, we also tested some M6s. I don't think many people would have a situation where they'd really be able to use an M6 that's only 10 millimeters high, but it was, as I say, just to give us a data point. But you can see, as we expected, the pull-off load of a M6 by 10 was pretty low. And you'll see in a moment, because I've got some more results for when we repeated this, that we've kind of confirmed that. So the observations from that part of the work was the size and the type of base plates doesn't really make any difference. In fact, if anything, larger base plates got in the way. They actually almost like formed a discontinuity in themselves. And when you think about it, you're kind of pulling that pad up, and all you really want is a big enough base plate, or whatever you're going to call it, that gives you a good purchase against that lump of GRC. So the bigger the base plate, the more you're kind of interfering, because you've got to kind of compact the material underneath it, and it probably means you're not going to get a very good adhesion with your, if it's sprayed GRC. So what we found was the height of the fixing, as you saw, made a substantial difference. The majority of the M10 fixings failed at forces above 10 kilonewtons, regardless of their height. So we found that quite an interesting result, because we thought even 10 kilonewtons is probably adequate for a lot of applications. So we decided to do some more tests on M8 and M10 stud anchor type fixings. So, of course, these are not available. Well, they are now, because we're making them. But I'll do a bob, get the advert in. But basically, we looked at a range of different heights, 10, 20 and 30 and 40s as well. Actually, these are just, and in an M8 and M10 size. we kind of considered that probably for a lot of people, going smaller than M8 isn't really very practical when you're giving a guy a bolt to put into it on site, etc. So they're the results we got, again, from putting those into a premix with 2.5% fibre. So we got these pretty substantial pull-off loads. The M8 and the M10 performed at a very similar level. Obviously we're not failing the fixing, we're failing the material around it. So both of these failed up at around 25 kilonewtons, and the shorter ones, the 20s, failed at about 20. As you can see, once we drop the size right down, the pull-out strength drops off considerably. And when you think about it, that's going to be logical because you've got some error in there. You might have a 10 millimeter high fixing, but you might have only compacted the material to a level of, say, 8 millimeters, and you've lost 20% of your embedment length. It's going to make a difference to the result. So having got that, we again made some observations. So the embedment depth of a fixing in a premix GRC is more important than the diameter of any base plate, but a base plate or an enlarged diameter at the base is recommended to ensure a reliable anchorage. And both M10 and M8 by 30 millimeter tool fixings yielded pull-out strengths in excess of 20 kilonewtons. Say 20 kilonewtons, when you consider that in terms of what most GRC products are in the UK anyway, is a lot of load. That you're not going to get many times when you need much more than that. And when I say about increasing the diameter of the base plate, all we did was take, in this case, a stainless steel washer and slip that over it, and hey, you've got something that's a bit bigger, so when the guys are packing the GRC around it, it just makes it a little bit easier for them. So now we came on to the next stage. So of course we've got these pull-out strengths, and we're sort of guessing what pull-off strengths might be. Of course we've cheated, you don't see this here, but we've already done some pull-off tests, and we know that in most cases the pull-off of a practical size of pad or embedment block isn't going to take more than about 10 kilonewtons. I gave you a clue in the last slide. But just to be safe, we've decided to go with the fixings that give you 20 kilonewtons or more. And we've now tested these in 100 millimeter square blocks, 150 millimeter square blocks, and 200 millimeter square blocks. So we made up some more, this time some templates, which we positioned on the back of some sprayed GRC, and we pulled these off. What was interesting, I was just showing this particular result, because what's interesting here is you can see that the failure isn't between the block and the back of the panel, it's actually just inside the panel. So we're back to stuff that others have mentioned, Bob in particular earlier, compaction and density and all that is pretty important. So even if we'd had a better adhesion with the back of the GRC, we actually have failed it before we ever achieved that adhesion. So as you would expect, we've got, sorry, I keep trying to use that. As you increase the size of the block, you increase the pull-off strength. But I mean, we're getting into quite big blocks now when we have 200 millimeter square. If you look at the stress, you notice it's not linear. The stress doesn't go up doesn't stay constant. It goes down proportionally to the contact area. So that was a bit of a surprise to us. We weren't expecting that. We then decided to change the test method a little bit, and we decided that we'd make it simpler for ourselves. So very briefly, we made up paper templates, and we put bonding pads like patties, like you'd use on a stud frame panel, and we used those to embed the fixings. And by using the paper templates, we've just controlled the contact area. So we've eliminated that variable. And then we've tested it in the pull-off, like you saw in the video earlier. And then we've got a load of results. So what's interesting, without going through all the individual results, most of the time the pad separated from the back of the panel. On occasion, it looked like it was starting to pull through. But what was the most interesting thing was this value of the stress, about 0.44. And if we go back to that first slide, look, the best value we got there was about 0.45 as a stress. So there's something going on there. We need to look at that a little bit closer. But it could well be that, it doesn't make any difference, keep making your pads bigger or whatever, you're never going to get a better stress at the interface than about 0.45, unless we can do something with the material. So just to finish off, the size of the contact area between the bonding pad and the sprayed GRC does influence the strength, but the relationship is not linear. The shape of the bonding pad or the embedment block is not significant. So the conclusions from all this was that pull-out strengths of M8 and N10 fixes embedded 20 millimeters and more in a premixed GRC with a fibre content of approximately 2.5% to 3% will yield strength capacities in excess of the requirements of most GRC product applications. The pull-out strengths of M8 and M10's fixings are generally much better than the pull-off strengths. And there may be practical reasons for using larger fixings, such as M12s, due to the geometry of the bracketry, etc. But most of the time, you're going to find that you could use an M8 or an N10. They've got plenty of capacity. And our recommendations are that have come out of all this testing is that, firstly, GRC manufacturers must carry out regular testing of fixings, in particular when manufacturing sprayed GRC products. I don't know, I'm not even going to ask for a show of hands, but from a straw poll we did originally, there weren't many people who even really appreciated that this could be a problem. Guidance on best practice is required for GRC manufacturers and designers, and probably this has got to come from an organisation such as the GRCA. The specifications for GRC products, again, they need to include some comment on how to fix fixings or how to embed fixings, and certainly we shouldn't have comments like use the same GRC as used in the product, not certainly for sprayed GRC. And manufacturers, in particular in hot climates, need clear method statements for attaching fixings to GRC products, in particular for sprayed GRC, in particular the time between spraying and then putting the bonding pad or whatever you're going to use onto the back of the panel. If that material dries out, if it doesn't pass the finger touch, you've got to rethink it. Now, that might not be the end of the world, but whatever. I'm just going to skip this because I explained that just now, and just talk a little bit about the future work. If I could just have 1 minute more, Benny.
Yes,
yeah?
Please.
So we're looking at shear testing. We've done a fair bit of shear testing already. What's generally interesting, I suppose, with this is that the shear failure is normally higher than the pull-off failure. So it's not a big area of concern, but we would recommend checking this once in a while. We've looked at what happens if you let the GRC dry and then try and stick a fixing on afterwards. Now, we just made up some sort of glue, let's say, cement polymer glue, and we got this, and I would say this is about the minimum you would expect to get. If we used a proprietary, say, concrete repair material to bond the fixings onto the back of the panel, and I think Bob's actually done this, you will get higher results. We also have just been looking at our own mixes to compact around the fixing. We found packing the fixing material around the fixing like this rather than forming a template might look very nice on a drawing when you draw that little box and whatever, but actually it's a pain, and what's better is really to hand pack it, because hand packing like that you do not end up with shadows on the surface. So, but we need to improve that mix design. That's the point, to make that more consistent. We've also really looking at the problem of edge distances where you cast these fixings in premixed GRC. As you can see from these few results I've put up there, we came up with a method which I can explain if anybody wants to hear about it later. But basically, we found that a couple of diameters of fixing away from the edge is yielding you far better pull-out strength than you would ever require. We've also done some tests on undercut anchors. If anybody, again, would like some information about that, we've got it. And finally, we've been looking at the problem of load-bearing ribs, where these might be attached to the back of a GRC panel and taking the load in shear, again, looking at the failure loads of those. But again, probably not a huge issue, but again, probably something that should be tested once in a while. So that's the end of my presentation. Thank you very much.